Good morning. I'm Altaf Hussain, former professor, Department of Chemistry, University of Dhaka. This is a S and A level chemistry lecture series. Today is 22nd lecture, and we will talk on enthalpy change and reaction kinetics. Okay, we have been talking about enthalpy change in last classes, last lecture, and then we finished talking about bomb calorimeter. I hope you remember that. Now we are talking further about enthalpy change, and that is what we say first of all. Law of conservation of energy. You know that we cannot create energy or destroy energy. That is what is law of conservation of energy. And this is also called first law of thermodynamics. First law of thermodynamics says the total energy of chemicals and their surroundings must remain constant. Then law of conservation of energy to enthalpy change. And that what Hess's law. That law says, I quote, the total enthalpy change in a chemical reaction is independent of the route by which the chemical reaction takes place, as long as their initial and final conditions are same. The states of the reactants and products must also be same, whichever route you follow. Okay, this is a diagram in which we are talking about this Hess's law. And we'll see in the next slide why we use Hess's law. Okay, well, if A is a reactant and D is a product, and if we go from A to D, which we call route 1, and it is delta H, okay, then this route can also be like this. From A, it goes to B, and then B to C, and C to D. That means this is another route, and this is another route, this is another route. Hess's law says that the enthalpy change in this way is equal to enthalpy change from A to B, B to C, C to D. Here we say enthalpy change, direct enthalpy change is delta H1. So delta H1 is equal to delta H2, delta H3, delta H4. That is what is Hess's law. Now, next slide says why we are talking about this Hess's law. Why? Well, you see, this model, this is a mathematical model. This model is on precise quantitative relationship between delta H, delta H2, delta H3, delta H4. The figure here we have already talked. Well, we know that we cannot measure directly enthalpy change by experiment. But this law, this model of Hess's can help us to calculate enthalpy change of formation, enthalpy change of reaction. Let's talk like this. This diagram, whenever we have a question in our exam about enthalpy change of a chemical reaction, what we do, we first draw a diagram like Hess's diagram, and then we see what are the enthalpy change it is given in our question, and accordingly we use this Hess law and find out the enthalpy change. So now I go with an example. You see, this example is a state like this, that we have to calculate what? Calculate the formation of propane at what temperature? At 298 degree Kelvin, given, and the following enthalpy change is given to us. Following enthalpy change, here it is. So propane, combustion of propane is minus 2,219 kilojoule per mole, that is given to us. combustion of graphite state, it is given to us minus 349 kilojoule per mole. And then hydrogen, combustion of hydrogen, standard combustion of hydrogen gas is given to us minus 286 kilojoule per mole. What is the solution then? The solution, what we have to do first, we have to draw an energy cycle, that is Hess's law cycles, or Hess's cycles, what we call. Then we see when graphite, that is this carbon 3, and hydrogen reacts together, we get propane gas. But then we can also have this route. What we have, that we get form carbon dioxide and water, and from this route we get also carbon dioxide water. So this is another. From there we can get carbon dioxide and water. From propane, we combust propane with oxygen, oxygen, we get carbon dioxide water. So according to Hess's law then, H2 is equal to H1 plus H3. So our H2 is this is the H2. So what do you do? We have 3 moles of carbon, 3 moles of graphite, let's say graphite, and 4 moles of water. We have here the standard enthalpy change of carbon, we do have, and then standard enthalpy change of hydrogen gas we have here. So we can, from 3 moles of carbon and 4 moles of hydrogen gas, we get the standard enthalpy change from here. So delta H2 is equal to 3 into standard enthalpy change of graphite and 4 into standard enthalpy change of hydrogen gas. We calculate this and we find out it is 2326 kilojoule per mole. Okay, what about H1 then? H1 is equal to again for standard enthalpy change of formation of propane. You see. So we know H1 now, and then H3. What is H3 then? From H3 is standard enthalpy change of formation also. So we can calculate and read this now. Then standard enthalpy change of formation of propane is taking this value and this value, and we find out that it is minus 107 kilojoules per mole. So again, I say that whenever we get a problem, what we have to do, we have to form an energy cycle like this and find out the given values of various reactant, and then we can calculate it and do it exactly quantitatively the standard enthalpy change of the reaction. Okay, next one, another problem. That calculate the standard enthalpy change of reduction of iron 2 oxide by carbon monoxide. Okay, then you see the values are given here again, and then we also again get our energy cycles. From here, it is standard enthalpy formation of iron oxide with carbon monoxide. That is, we reduced it and we get iron. So the solids, say iron and carbon dioxide. Okay, we can do this also. Iron and oxygen plus graphite, we go to this. And we have also, we go from this reaction, we go to this. So again, we have energy cycle changes. And from that, these values, we find out what is the standard enthalpy changes for the reduction of iron 3 oxide by carbon monoxide. We take these values, calculate it, calculate it as per the Hess's law, and then we find out that standard enthalpy formation of iron, standard enthalpy change of reduction of iron 3 oxide is equal to then minus to 828 kilojoules per mole. This is what all we have done by getting this values given to us, and thereby we find out the standard enthalpy changes of this problem. This problem, what I say, reduction of iron 3 oxide by carbon monoxide. Now we see that we can, though we indirectly we can measure standard enthalpy change, but this Hess's law, using Hess's law, we can also quantitatively with this model find out the standard enthalpy change of a reaction, or either formation or of a reaction or so on. Up to this, we were talking about enthalpy change. The next problem, or next chapter of the syllabus is reaction kinetics. So we start the new chapter in AS syllabus, that reaction kinetics. And to do this, what we have to read the subsection of the chapter is reaction rates, how we measure reaction rates, which factors are affected to get the reaction rate, collision, what is collision theory, Maxwell-Boltzmann distribution, explaining the effects of concentration, pressure, surface area on reaction rate, explaining the effects of temperature on reaction rates, explaining the effects of catalysis on reaction rate. These are the points to be discussed as per syllabus of AS level reaction kinetics. Well, you see, we do know that some reaction occur very fast, as well as we do know that some reactions occur very slow. Well, we have been talking about chemical equation. You see, I go to the next slide and come back again here. You see, this is a chemical equation. What we do, we take calcium carbonate solid and then aqueous hydrochloric acid. What we get calcium chloride, carbon dioxide, and water. This balanced chemical reaction doesn't tell anything about reaction rate. We know this is a balanced reaction and it's nothing about reaction rate. So what is then the reaction? Is it a fast reaction, slow reaction, or very slow reaction? That's what we have to study, and that study is called reaction kinetics. Why you do that? With the experimental data of rate of reactions, we know how the reaction takes place. That means we can deduce the mechanism of reaction by using the kinetics data. Well, let me take the last slide. Okay, you see, this is a firework, and this reaction, chemical reaction, is too fast. Okay, this is, you can see, a rusting process of a shape, and this is rather slow reaction. Therefore, ionic precipitation reactions are very fast. Even explosions reactions are even faster, but rusting or corrosion are generally slow process. It may take some years. Okay, then we come to this. You see, we can also have computer graphics to see how we can engineering that reaction and do atoms level, molecules level, ion levels during chemical reaction. What happens in the atom models, atoms, molecules, and ions during chemical reaction by studying reaction rate. You see, this is a graphic presentation of a methanol. This is methanol. What is it? We are using a catalyst, and that is synthetic zeolite. This is synthetic zeolite. And this methanol, with these, we can have even new fuel from methanol. So chemists are continuously doing research to get atomic scale very well about atomic scale of the reaction mechanism and even developing effective catalysis. Okay, so next slide. What now? Now, what we were talking that we have to find out reaction rate, and we have to measure it also. Not only find out, we have to measure this reaction rate, and we have to have the data and can predict how fast the reaction is going on and how slow the reaction is going on. What is that reaction rate? How do you define it? The change in amount of reactants or products with time. That is what is reaction rate. Change in amount of reactants or products during reaction with time. We call it reaction rate. Okay, what is the unit of reaction rate? When we call change of amount of reactants, that our reactants, we mean this concentration of the reactants and also concentration of the product. But if we remember, and we do remember, the concentration we expressed in mole per dm cube. Okay, so if the rate of reaction and then unit of time is expressed in second, therefore mole of unit of the reaction rate will be mole per dm cube per second. Okay, now if we have a very fast reaction, we definitely time is taken as second or millisecond, etc. But if the reaction is very slow, the unit for time, we may use even per minute or even in very slow case, per hour. Okay, well, as mentioned in the last slide, the balanced equation do not give us any information how quickly reaction occurs or how slowly it occurs. So rate of reaction has to be known. The chemists are doing always very careful about knowing the rate of reactions under various conditions. We have to remember that rate of reaction depends on various conditions. Okay, so let's say this magnesium, a solid magnesium with aqueous hydrochloric acid. What we do, we get magnesium chloride, aqueous magnesium chloride, and hydrogen gas. Okay, any one of these, if we measure any one of these, how the rate of any one, that means rate of loss of magnesium. We can measure rate of loss of magnesium. We can measure rate of loss of hydrochloric acid, or we can measure rate of formation of magnesium chloride or rate of formation of hydrogen gas. And thereby, from there, we can find out the rate of reaction. A very simple experimental set here is this. We keep the metal here, that is magnesium here. We add hydrochloric acid here, and then we get hydrogen gas. We measure the hydrogen gas, and then we can find out the reaction rate. Well, here we showed a measuring cylinder. This is water bucket, and the measuring cylinder. Hydrogen gas goes into the measured cylinder, and then we find out the volume of hydrogen gas. One can also use gas syringe to get the volume of hydrogen gas. So, well, this slide shows us different curves. One is volume of hydrogen gas in y-axis, and then x-axis is the time. And therefore, from here, we can find out the reaction rate. Another is the product concentration of the product, and then time. From this tangent, this curve, we can find out also reaction rate. Here we can see how fast a reaction goes, and then we can also get the number of amount of product X mole from this curve. Well, I will definitely discuss these slides again in the next lecture a bit detailed, and we know more about reaction kinetics. We have to learn further points on reaction kinetics to understand a little bit develop concept of reaction kinetics and why we need to read reaction kinetics very carefully. Thank you very much for this lecture. We will see again in the next lecture with reaction kinetics. Thank you.